Alright, for lesson 13.3 we're going to address periodicity and symmetry, and what this is going to lead into are the graphs of the trig functions, and it will allow us to look into their symmetry and how long it takes for those graphs to repeat themselves, which is the periodicity. So we'll start off this lesson. We'll just look at some general graphs and things and try and get the idea of both of these things. So for a periodic function, that is going to be a function which we're going to call f. If you remember function notation, we'll call this function f, and it is going to be periodic if for some positive constant value, which we'll say is p, when f of x plus p has the same exact value as f of x did. So what that means is that function is going to begin to repeat itself after we add certain values to it. So it's going to occur over and over and over and over again. Okay, that smallest such value for p is going to be called the period of that function f. So the period will be that cycle with which that graph repeats itself. For example, the sine of, let's first look at the sine of s. Okay, and let's say that that s value were up in here. That's going to be some x and y value. So let's see here. Let's use our highlighter for a second. Okay. So, whoa, that was a little large, wasn't it? Let's ratchet that down a little bit. So, our highlighter right in there. So let's call that value s. Okay. Well, that's the same value. That sine value is going to be my y value right there, right? Well, that's going to be the same as if I had, let's go back to that highlighter, as if I had gone from there and went all the way around. And if I go all the way back around, okay, and that is s plus 2 pi, right? Okay. So that sine value of s is the same as the sine value of s plus pi because they are coterminal, right? So that green was s plus 2 pi there. Okay. Same thing for cosine, right? The cosine of s and of s plus 2 pi is the x value in there. That's what we learned from last time. So the cosine of s plus 2 pi is the same as the cosine of s. And we're going to say that that period then, since it starts to repeat itself after 2 pi, that's the smallest value I can add, and begin to repeat itself. So that period is going to be defined as the time or the interval to complete one cycle or revolution. Okay. Alright. Now, when we talk about, we're going to talk about functions as they apply to their symmetry, they're going to be either even, odd, or neither. So the first thing we'll do is take a look at an even function. An even function is going to be even if some value f of x is equal to f of negative x, meaning if I plug an x in or if I plug a negative x in, I'm going to end up getting the same value. Okay? So when a function f is even, its graph is going to be symmetric with respect to the y-axis. Wait for my pen to stop thinking here. Y-axis. That is, if xy is on the graph of f, then what else is going to be on that graph? Well, if it's symmetric with respect to the y-axis, then negative x y will be on that graph. What you want to think about here is these graphs will be symmetric. It's like you can fold that paper over at the y-axis, so you can bend that paper over and it will be on top of itself if you fold it at the y-axis. That's what being symmetric there means. Okay, so let's take a look at these. If the cosine of s, let's see here, cosine of s, let's say that s is up in here. Okay, so the cosine of s there, if that's x, y, we know that the cosine is my x value, right? Well, negative s, if we went up this direction, to get negative s, we go down, right? Well, that value. So that would be negative s. This up here was positive s, right? Negative s would be this direction, and those coordinates it would still be a positive x, but it would be a negative y, right? Well, the cosine value is x, so therefore cosine is an even function, because when we plug in a value and its opposite, we get the same value for both. An example of this would be like if we had f of x equaled x. Oops, let's make that red. Sorry. If f of x equaled x squared, then if I plug in a negative x into that, well, I'm substituting in for x, so that would be a negative x squared, which I know negative x times negative x equals, so that's negative x times negative x equals positive x squared, right? So that is also an even function. Alright, so that's a look at even functions. Now let's take a look at a function that would be odd. A function is odd if f of x, actually, sorry, if f of negative x will then result in the opposite of f of x, or negative f of x. And we'll illustrate the difference here down below. When a function f is odd, its graph is symmetric with respect to the origin, which also means that it is symmetric with respect to both the y and x axis. When it's symmetric with respect to the origin, when you're thinking about this visually, it's like you have to fold that piece of paper over the y-axis and then over the x-axis, and then it will be the graph will be on top of itself, and we'll illustrate that in an example here a little bit later. If we look at this, with the same lines here. Oh, and what this means is if we have xy on the graph, then so is negative x, negative y. Okay, so when our input is the opposite, then we get the opposite of our output. Whereas up here, when our input was the opposite, we got the same output, right? So an example of an odd function is sine. Sine, if this is s, we know that's xy. Sine is equal to the y value, right? So, but the sine of negative s, remember, negative s is down here. Disregard that circle there. I don't know where that came from, to be quite honest. That is x negative y, right? So the sine of negative s is actually negative y. So when we plug in the opposite value, we get the opposite result, and that means it is an odd function. An example of an odd function would be something raised to the third power, because we know that when we substitute in negative x for that, that is the same as taking negative x times negative x times negative x. And we know that when we take a negative times a negative times a negative, we get, whoops, it's x cubed, right? A negative x cubed. So that would be the opposite of what we get up here when we plugged in a positive value. Okay, so those are examples of odd functions. Cosine is even, sine is odd. Functions do not have to be even or odd. They can, in fact, be neither. All right. Now we'll go ahead and take a look at some examples to kind of clear some of this up for you, if you're having any questions so far. So let's take a look at this graph on the following page. Part of the graph of function f having period 2 is shown below. So you can see this graph with period 2 because I went from negative 1 all the way to 1. Well, that's 1, 2. That period is 2. Okay. It wants us to graph f in the interval of negative 3 to positive 3. So that means I need to continue this graph over to, let's see, whoops, stop thinking here, over to 3, and over to negative 3. Okay. So let's go ahead and essentially, if it's telling us that the period is 2, that means I see one period right here. So now I should just have to repeat this graph. So when I'm going to do that, I simply want to repeat what's already there. Whoops. There's that end of it. And there is that end of it. Okay, so I've repeated that graph. So now I've got an interval from negative 3 to positive 3 because I had to go 2 more there, so I knew I needed to complete another period or another complete graph right there. And now tell whether it's odd, even, or neither. Now when I'm going through that process, I want to look at some points. So if I have a value right here of 1, 1 is that point, right? And then I've got another point over here at 3, 1. To determine whether it's even, odd, or neither, I want to look over here at these points. So that point is negative 1, 1, right? negative 1, 1. And that point is negative 3, 1. Okay. So now that I'm looking at that, and if I look back at my previous notes where it said if it's even, if I have xy, I should have negative xy. Well, that looks like what I have. If I have 1, 1, I should have negative 1, 1. If I have 3, 1, I should have negative 3, 1. And you can also tell that if I folded this over this y-axis right here, wouldn't this graph be on top of itself? What is over here would be on top of what is over here. If that is the case, then that particular graph is even. Okay. Now, down here on the next one, part of f is shown below. I've got this part of f. Graph f between negative 2 and 2, assuming f is first even and second odd. So what I'm going to do here is I am going to graph it first in red. Okay, so I'll do a dotted line in red if it's even. So if it's even, I should be able to simply mirror this image, right? Let's draw these values in. I've got a 2 here and a negative 2 here. That's where I want to go with it. So I should be able to just mirror this across the y-axis. Okay. So when drawing that, I can do that right there. That's pretty easy to see. Okay. If you had some confusion there, you could go back to our points up here. If I had, and just consider some of these points. I've got a point there at 1, 1, and I've got a point here at 2, 0, right? Well, if it's going to be even, then I should have a point at negative 1, 1, and I should have a point at negative 2, 0, right? Does that make sense? And that's what I do in fact have here for these. Okay. So if I didn't see that visually, I could have just drawn those points and then connected the dots there. Now let's take a look at the odd graph. Now the odd one I think is hard to visualize because you have to, it's symmetric about the origin, which means you have to fold it across the y-axis and then the x-axis. So I folded it across the y-axis here. Then when I fold it across the x-axis, this will actually come down here. So when we're starting from scratch, I think it's easier to take a look at the points. And if you remember, on the odd graphs, if I have x, y, I should have negative x, negative y. So when I go here, if I had 1, 1, I should have a point at negative 1, negative 1 right there. Okay, negative 1, negative 1. And if I have a point at 2, 0, I should have a point at negative 2, negative 0, but we know that there is no negative 0, so that's just 0. So I've got a point there. So I can tell now that this odd graph would continue in this fashion right here. Okay? So you can think about those as two separate problems there. One, I drew an even representation of that graph. The other, I drew an odd representation of that graph. Okay. So that's how we look at things graphically when we're talking about period and the symmetry and whether something is even or odd. On this last page, we're going to talk about how we will determine whether something is even or odd using just the equation. Now, okay. take a look here. Let's go back to my pen. Let's do this first one in, I don't care. Let's go green. So, how we determine whether something is even or odd is we take our input, and when we plugged in x, this is what we got. So we want to know what happens when we plug in negative x. Now when you plug in negative x, I'll make a suggestion to you. Always put it in parentheses. So negative x would go in the place of x, and that is squared, right? So negative x, and that was squared plus 2. So let's look at what happens here. I plugged in negative x, right? Well, when I square a negative value, negative x times negative x would be x squared, right? And negative x times negative x would again be x squared. I didn't do anything to this 2 down here. So it appears to me that I get the same value that I got when I plugged in x as when I plugged in negative x. Therefore, that means that that particular equation or graph of that equation is an even function. Okay, so it would be symmetric about the y-axis. Let's go look at g of x over here. Well, to determine whether it's even or odd, we're going to plug in a negative x. So negative x cubed minus, here's where it's very important that you put these in parentheses, because you'll see that when I plug in negative x cubed is in fact going to be a negative value, right? Negative x cubed. And then when I subtract a negative x, I end up with a positive x. And you'll notice, do I have the same values I got up here? No, I have the opposite values. X cubed up here, negative x cubed down here. Negative x here, positive x here. If it results in something that is the opposite, remember that that is an odd function. And lastly, I've got h of x over here. When I plug in negative x into this value, I end up with negative x squared plus 2 times negative x. Well, h of negative x simplifies. Negative x times negative x would be x squared, which was what we had there. But 2 times the negative x would be a negative 2x, which is the opposite. So this term is the same. This term is the opposite. So it's neither the same nor the opposite, right? I've got one piece that's one and one piece that's the other. Therefore, this would be neither even nor odd. So it is not symmetric about the y-axis or about the origin. The homework we're going to work on, or the problems we're going to work on today after reviewing this video, are going to be 1 through 9 on the oral exercises and 2 through 20 even on the written exercises. Thanks for following along. Bye-bye.